In a chemical reaction roadmap, we want to show the sequence by which bonds break and form to go from reactants to products. Experiments are performed to determine the rate law of a chemical reaction. The rate law is used to predict a reaction mechanism. A reaction mechanism tells us the sequence by which bonds break and form going from reactants to products. We're going to use curved arrows to show how those bonds break and form. Most organic reactions are polar reactions, so we will want to identify the nucleophile and electrophile and then draw a curved arrow from the nucleophile to electrophile to show bonds breaking and forming. This picture shows the 4 types of organic polar reactions. We will want to identify the nucleophile and electrophile in each reaction. For example, in the acid-base reaction, the nucleophile is the base and the electrophile is the acid. We will identify the nucleophile and electrophile in the other reaction types later. It is very easy for a beginning organic chemistry student to show arrows going all over the place. What you want to realize is there's only a few bond breaking and making processes in organic chemistry. Those processes are described here. Identifying structural features help. For example, alpha carbon, beta carbon, and leaving group. In these 3 steps, reactants and products are shown. Stop the video and use curved arrows to show how bonds break and form in each step. In step 1, that's the proton transfer or acid-base reaction. In step 2, that's called ionization of a leaving group. In step 3, that's called nucleophilic attack. Let's try another one. You're given a reactant and a product. Stop the video and use curved arrows to show bonds breaking and forming. So here's what's happening. And this is a proton transfer reaction. Let's try another one. Stop the video and use curved arrows to show how each product is produced. So here's what's happening. The type of nucleophilic attack is a carbon bonded to a leaving group, and this is an example of a substitution reaction. Let's try this example. Stop the video, use curved arrows to show how each product is formed. So here's what's happening. The type of nucleophilic attack is a nucleophile attack in H bonded to a beta carbon, and this is a type of elimination reaction. This reaction is an addition reaction, which is the 4th type of organic polar reaction. Stop the video and use curved arrows to show how each product is produced. So here's what's happening. In the first step, the Klein textbook describes it as a proton transfer reaction. The second step involves a nucleophile attacking an electron-deficient species. That electron-deficient species is the carbocation. Review your formal charge rules to make sure that carbon has a +1 charge. Carbocations are classified as either primary, secondary, or tertiary. A primary carbocation has 1 carbon bonded to the carbocation. A secondary carbocation has 2 carbons bonded to it. Tertiary has 3 carbons bonded to it. So stop the video and answer these 2 questions. So here are the answers. In these 3 reactions, you're given the reactants and the curved arrows. So stop the video and draw the product of each reaction. And the answers are: note that reaction B forms the carbocation. Another type of bond breaking and making process is a carbocation rearrangement. A carbocation can rearrange to form a more stable carbocation via a hydride shift or alkyl shift on the adjacent carbon. The 1,2 refers to carbon 1 where the carbocation is, and carbon 2, which is the adjacent carbon where the hydride or alkyl group is. So stop the video and answer this question. And the answers are: a secondary carbocation rearranges to another secondary carbocation, so there's no increase in stability, so that reaction will not occur. The rearrangement that can occur is this one. A tertiary carbocation forms. In 2016, this carbocation rearrangement mechanism was proposed. So let's practice. Stop the video and determine which compound or compounds will undergo a rearrangement. First, classify each carbocation. Then see if a rearrangement can occur via a hydride shift or alkyl shift.